great pleasure to be here. I like a lot Melbourne. And before I start, let me say, interrupt me whenever you want. Don't keep your question at the end of the talk. Now, what I want to discuss with you today, it's a rather simple question that turns out not to be that simple, which is basically what is the distinction between solids and liquids? And I will try to bring you with me in a journey discussing this question in different contexts, from low energy physics to high energy physics. Let me start with what the question. So first of all, is this a trivial question, or are we asking something which is actually deep? As you can imagine, since I'm here trying to speak to you, the answer is that this is not a trivial question, despite what most of the people at the airport think. So I invite you, as a little game, to think just for 30 seconds about what would be the best answer that you could give about the difference between a solid and a liquid. So meanwhile, you think, since we are in the era of Google, AI, ChatGPT, and whatever, the first thing that every one of you with a laptop in front will do is searching in the web. And of course, in the web, you can find answers. And apparently, there is a website which is called the Difference Guru. We compare things. So I asked the guru, what are the differences between a solid and a liquid? And the guru proposed me a bunch of answers with different level of context. So let me go very quickly through some of them, because we will discuss if they are actually valid or not in the following slides. So the first and maybe the simplest answer is that a solid has a defined shape and the volume. A liquid takes the shape of the container where you put it. This is a property of, if you want, the macroscopic properties. Now, the second difference, and this is a bit more subtle, is related to the dynamics. And as you can see, in solid, we usually talk about vibration, while in liquids, we are more talking about loosely motion that basically convert in something which is diffusive or relaxing, like some colors in some water. Then, of course, we can talk about properties, and we can talk about the difference between properties of solids and liquids, and this is what it is. And then, of course, you can also discuss transitions between the two, and this is basically what the last term is. Now, let's go through the first of these answers. So accordingly to the first answer, cats are liquid. Well, we can discuss if this is a good answer or not. And even more, I mean, apart from this joke, there are more contexts where the first definition fail, and this is like water in microgravity. So you can see this water definitely doesn't take the shape of the container. So is water a solid, a liquid, or does it depend on the condition? So definitely the first answer given by the guru, it's not really satisfactory. Now, apart from these initial jokes, one possible way to distinguish solids and liquids is looking at structure. And as you can see, I mean, solids are usually thought as something very ordered, where the particle wants to sit in preferred position, which are somehow periodic or distributed in a periodic pattern accordingly to the lattice structure. On the other side, completely the other side, you have gases where the particles are basically free. You can completely ignore any potential energy. They're just moving around. And in the middle, you have liquids. So liquids are dense, so they're not so dilute like gases, so interactions are important. But they're not so dense as solid, and definitely they don't share a very clear, at least, order pattern as solids. And then this seems to be rather clear, and we will see ways to actually make it even clearer. But then there is always the question behind, which is a big question, if you want, in soft matter, which is how much structure actually determine dynamics. So can you have a one-to-one correspondence or connection between the structure that you see and the dynamics that you actually measure when you deform these systems? Now, the concept of order, of course, is much more profound than just looking at it, looking at the sample you have. And at least in a condensed matter literature, one, let's say, good way to speak about orders is to compute the radial distribution function. So this is a very simple concept. Imagine that I'm your tagged particle, and I'm just looking in circles around me, and I'm counting what is the probability of encountering one of you. And as you can imagine, if this probability is flat, it means that basically you are completely distributed in a disordered way around me, probably like at the station. But if I encounter some pattern, so after a certain distance, I see that the probability is actually picked, it means that you are not randomly distributed around me, but there is some kind of order in the periodicity. And that's what you see here. So this is basically argon. And you can see the difference between the liquid and the solid. So the solid has peaks that are periodic and corresponds basically at the pattern, at the lattice of this structure. While liquids, they have a first peak, which is a bit less intense. This is just basically your first neighbors, so the first neighbors around you. But then you can see that when you go away from me, this order becomes weaker and weaker and weaker. And in jargon, we say that solids have long-range order, so this order is maintained up to infinity, while liquids have short-range order, meaning that there is order only up to the first neighbors, if you want. So again, we can be more abstract or more formal and more theoretical. And order can be related to spontaneous symmetry breaking, which is, of course, a pivotal idea in modern physics in many different fields. So what is the idea? The idea is simple. So a symmetry is spontaneously broken when the state breaks basically the symmetry of the system itself. So the easiest example that I can think of is you can think about a plane which has basically rotational invariance around, and you can put a pencil there. And obviously, if you wait for the system to go in the preferred position energetically, this pencil will fall at a certain point, meaning that the states, which minimize, if you want, your potential, breaks the initial rotational symmetry. Okay? So this is just a cartoon to basically explain this spontaneous symmetry breaking. And why this is relevant for solids, because solids, and actually many of the properties of solids, can be understood by saying that solids break spontaneously translational symmetry. And from a practical perspective, this just means that, again, the atoms do not want to sit randomly. There are some preferred positions. Now, this was about structure. So you see, we have basically some rather well-defined concepts of order that we can apply to structure, to divide basically liquids and solids. And then you want to go through dynamics. So if you go to dynamics, the first answer that you will give about the difference between solids and liquid is that a liquid flows, and the solid does not. Now, as you can see, already in the Bible, they knew that this is not totally correct, in the sense that if you wait long enough, everything flows. So this is a famous sentence that Marcus Reiner, one of the pioneers of rheology, the study of the formation of soft matter system, said. And you can even define a number, which is a Deborah number. So at the beginning, when I started working on this, I thought that Deborah was a big scientist. And apparently, actually, she's not. She was a prophetess in the Bible. And, but the main idea is that, of course, whether something flows or not depends on the time that you are measuring or the time of observations. And there is one example which I think is quite practical, which are these beautiful stained glass windows, color that you can see in cathedrals in Europe and probably also here in Melbourne. So this is experimentally tested. So if you look at the thickness of the glass at the bottom, you will see that the thickness is actually larger than at the top, meaning that this glass is actually flowing down under the force of gravity. And of course, you will not see it flowing if you just stay in front of it a few minutes. But if you measure it, you will see that. So now, this is a bit the introduction. Now I want to tell you why, if you want, solids are better understood and usually more discussed than liquids. So the reason is, so why crystalline solids are simple? There are two different reasons, and the main, maybe the most important reasons, is that the atoms in a solid move very little from their positions. So even though the interactions between the atoms is strong, they don't move a lot. So what this means, as a theorist, this means that I have a small parameter. And whenever a theorist has a small parameter, he's happy, because then I can build some perturbative theory in this small parameter. And this is exactly what elasticity theory is. Okay? So to make it a bit more precise, imagine you have your solid with your atoms. So you can imagine that these atoms vibrate because of thermal excitations, or you are literally deforming it. And each of them will move a bit. And you can define a vector that is called displacement. And then using the fact that this displacement is small, and I can define actually in a better way small compared to what, Then I can write down basically a theory, which is the theory of elasticity, which is based on what is called the strain tensor. So here you can see also another thing which is interesting. Forget about the details, but just keep in mind that this object is a derivative with respect to the displacement. And this is basically encapsulating the fact that there is some translational symmetry. So you can just shift this vector as much as you want globally. This will not make absolutely anything. So the energy of these things will not change if you just move it up and down. That's why the derivative actually matters. And then you can write what is called elastic energy, which is basically just a quadratic functional of this strain. And thisCijkl, it's a tensor that determines basically how rigid is the system in the different directions. So these are the elastic moduli. Now, to tell you also that the fact that the displacements are small is a characteristic of solid, let me mention that there is a very famous criterion for determining when the solid melts. It's called the Lindemann melting criterion. And it's based exactly on this assumption. It's based on the assumption that if the atoms goes too far away, the solid will melt. Now, another thing which is important is that in all of these, we almost always assume an harmonic potential. And this is also important because anharmonic terms that will enter will complicate a lot the situation. And as we will see in a second, for liquids, the harmonic potential, let's say, prescription completely fails. Now, a bit more of formulas to scare you. So what can we learn from this basically solid description? Well, then we can just apply what is called the constitutive equation. So the fact that the stress is proportional to the strain. That looks very complicated, but it's nothing else than Hooke's law, if you want. So the force of an elastic band is proportional to the displacement, and that's basically what you see. And this object, again, determines how stiff is this elastic band, basically. And then, well, you take this Hooke's law, and you plug it in Newton's law, and you get your equation of motion. This is just, standard classical dynamics. And what you learn is that because of this structure, solids have excitations, which are called phonons, which disperse linearly. So their energy or their frequency is linearly proportional to the wave vector with a certain velocity. And of course, they are damped, so they don't propagate forever. That's the reason why I use a mic, basically. Now, if you want to be more abstract, again, you could have skipped completely all these formulations, and just from the fact that I told you that solid breaks spontaneously translation, you will have derived the existence of these modes. Because these modes are nothing else than the Goldstone modes of the translational symmetry that you broke. And indeed, they are protected by symmetries. So whatever solids you take, these will be always massless in particle physics language, meaning that when you send the wave vector to zero, the energy will go to zero. Now, this is a lot of blah, 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 but then if I'm an experimentalist or I'm somebody that wants to use a solid, I care about the properties of the solid. And what are the main properties of the solid that I care of? Well, there are at least three that for the moment I want to discuss with you. One is what I just said. This is the phonon dispersion. So you can clearly see here, this is the frequency as a function of the wave vector. And you see that there are linearly dispersing modes, which are massless. And these are the phonons. And then, of course, there are many more modes, which are not, let's say, low energy modes. And that depends on the system. And let me also say that this is not just a theory thing. This you can do a scattering experiment, and you can actually measure these quantities. You can see these modes acting around. Now, you could ask yourself how many modes I have per frequency or per energy. And then you will end up computing what is called the density of state. And the density of state, this is a famous result due to Mr. Debye. The density of state in a solid is quadratic in frequency at low frequency. And here you can see this is a comparison between the Debye model. This is the Debye model. And this is a real experimental data from copper. And you can see that in the low energy region, indeed, there is this omega square law. And from now on, I would call this the Debye law. Now, another consequence of this Debye law is that if you look at the specific heat of a solid, the specific heat of a solid will grow with a power law, which is T to the cube for bulk solid, which is a direct consequence of this power here. Okay? And then, of course, it will saturate in what is called Dulong-Petit law. And let me also emphasize that this kind of curve, it's highly universal. So if you basically reduce the temperature by what is called the Debye temperature, which set the microscopic scale, all solids will just overlap on the same curve. So this is quite amazing. Now, this was all the introduction about solids, and this is all textbook stuff. But what about liquids? So how much of these three properties we understand in liquids? Now, in liquids, the situation is more scary. And this already started from Landau. So Landau, in his famous books, at least in one of them, mentioned not once, but twice, that for liquids, the story is impossible. And you can see clearly here, it's impossible to derive any general formula giving a quantitative description of liquids. And here it says even that do not allow. And the reason why he mentioned is that liquid does not have a small parameter. Why? Because the interactions are still strong, so it's not a gas, because the atoms are still quite close to each other. But also the displacement are not small, because the atom can move quite a lot and rearrange around. So there is no small parameter, and then as a theorist, I don't know what kind of theory I'm going to write in a perturbative fashion. It's a non-perturbative theory, and non-perturbative theories, of course, are much more complicated than perturbative one. Now, Granato, which is another big guy in the topic, mentioned that he lived in constant fear that some student might raise his hand and ask, how about liquids? OK, so this is a real thing. And so to summarize, the point is that the collective modes, the thermodynamics properties of liquids are still very poorly understood, and they are still debated right now. OK? So what can we say about liquids? So let me first say one thing. I'm Italian, and in Italy we have this sentence, which is quite common, is like getting lost in a glass of water. And we usually mention to say this, I mean, don't get lost in something very trivial or don't waste time for trivial things. And I have to say that, we're usually right, but in this case, we're definitely completely wrong, because nor the glass nor the water are simple things at all. Now, what is the plan for today? So the plan for today, I want to discuss with you how much we know about collective excitations, density of state, heat capacities, and then some universal physics related to the properties of liquids. So let's see how far we go. So liquid dynamics. So the oldest idea about the description of the dynamics in liquid, of course, starts from the solid picture. And the idea is the following, is that the potential of a liquid is a very complicated anharmonic potential with many minima, many maxima, saddle points, and whatever. So atoms, what do? The atoms, they will oscillate for a certain time around the local minima, like in a solid, if you like. But then after a certain point, they will jump away, they will cross a potential barrier, and they will rearrange somehow. And the simplest model that you can think of is that there is a characteristic time that I call tau, which is, if you want, the average time for jumping these barriers. And practically, you can think this is the average time of basically rearranging the atoms in your liquid. Now, if you accept this picture, which, by the way, was introduced by Frenkel and Zwanzig, you can immediately see that there is a scale here playing a big role, which is what is called the Frenkel frequency, which is the inverse of that time. So now, if you're looking at frequencies which are much larger than that time, it means you're looking at very short time scales. These things that didn't have time to jump. So it's conceivable that it's behaving alike, or at least very similar to a solid. But of course, if you're looking at late time, which is low frequency compared to the scale, then of course you will see something very different from a solid, which is mostly dominated by this rearranging dynamics. So this is if you want, the assumption or the hypothesis of these theories. Now we want to see how much of this hypothesis actually is realized in real liquids. So there is more. Because actually this idea of mixing vibrations and relaxation is very old. It already originated in the famous Maxwell viscoelasticity theory. So Maxwell realized that, OK, we have a solid which is perfectly elastic, at least idealized system. We have a liquid which is a perfectly viscous and diffusive system. But of course, if you look at some general system in nature, it would be a combination of the two, which is basically a viscoelastic medium. And what you can do, you can basically mathematically force this, let's say, coexistence of these two type of response. And here I just show one way to do it. This is a very practical way. So you can start basically from Navier-Stokes equations. So these are linearized Navier-Stokes equations that determines basically the dynamics of your fluid. And then you can introduce this time tau, which is, again, formally similar to the time that I was discussing before. And this introduces some reactive response. And if you do so, you will put it inside here. You will get one equation, which looks like this, which is actually called the telegrapher equation. I will show you in a second why it's called that way. But let me discuss very briefly with you the equation. So forget about the details. But the important thing that you can see here is that there is a competition between the terms that has two derivatives in times and one derivative in time. So if I kill completely these terms here, you can immediately recognize that this is a wave equation. So you will see something that vibrates around. This is a wave equation. Now, on the contrary, if I kill these terms, this is a purely relaxing exponentially decay. Okay, so these are the two types of dynamics, and what you can imagine immediately is that depending on the strength of this tau compared to your time derivative, you will basically have one or the other winning. So mathematically, what I'm actually doing here is nothing else than writing down in mathematical terms the idea of Frankel that there is a competition between vibrating and jumping. That's basically what it is. Now, this equation is rather simple, and so let me first say why it's called the telegrapher equation. It's called the telegrapher equation because it was discovered for the first time by Heaviside, and it's actually the equations that determine the dynamics of currents in the circuit of the telegraph. So that over there is a telegraph, and if you actually do your exercise, your homeworks, and you solve the equations for the currents in that thing, you will find exactly the equation that I just wrote. Now, that equation is very general. It appears in millions of different fields. And here we wrote a review where you can see all the different fields where it appears. So for example, I know that many of you do astrophysics. This is also an equation that appears in magnetohydrodynamics, for example. So you can find it there. Now, if you solve that equation, what do you get? So you just go to Fourier space, and you get this simple quadratic equation. You solve it, and you get your solution. Now, let's look at the solution. Let's look first at the real part. So there is a square root type, and then you see that if the wave vector is large enough, this square root is real, and if the wave vector is small, it's actually imaginary. So this is telling you that the frequency of this mode will be purely imaginary at low frequency, so at late time, meaning that these things will just relax. But if you go at high wave vector, so at short distances, actually you will see a mode that starts to propagate. And you see that if you go at very large wave vector and very large frequency, you see that basically there is a linearly propagating mode, exactly like the phonons in solids. Okay, so if you want, what this is telling you is that there is a scale, not only in time, but also in space, that determines a crossover from something that behaves like liquid-like, late time, long distances, to something that behaves more like solid-like. And this is basically the cartoon. So you can see that there is a transition between something which is relaxational, like basically just water ripples, and something that looks like very similar to vibrations in a solid. And this transition occurs in a specific way through a transition between an overdamp to an underdamp regime. And you can actually check that, at least qualitatively, these kind of equations, it's in complete agreement with the Frankel criterion. So if you put basically tau, this would be tau. So frequency above tau are here. So you see that there is something propagating. Frequency below tau are here. You see that there is something that does not propagate. Now, don't get fooled by the fact that there is a real part. The fact that there is a real part doesn't mean immediately that these things propagate, because you need the imaginary part to be smaller than the real part to see actually oscillations. So here there's nothing propagating yet. Okay? Now, this is all theory, so I'm a theorist, so of course I put a lot of emphasis on this, but then let's see if this theory is actually realized somewhere. So one of the first, let's say, experimental proof that Frankel's idea is at least qualitatively correct, was given in this nice paper. So what they did a neutron scattering experiment in the same system in the liquid phase and in the crystal phase. So what you see here are the black is the crystal phase and the blue is the liquid phase. And you see that there are peaks. So each of these peaks represent an excitation. So you are actually probing an excitation of the system. These are different wave vector. And you see these are not small wave vector, actually. These are already large wave vector. And what you see is that both the liquids and the solid have the same type of excitation, if you want. So you see the same peak. The only difference that you see, of course, is that intensity is different. The liquid is more disordered, etc., and is a bit broader. And this is what you can see. The only relevant difference between the liquid and the polycrystal appears at broadening of the excitation. So if you want, this is the experimental proof, or at least experimental indications, that at large frequency and wave vector, liquids and solids are actually much more similar than what we expect. Now, you can do more. You can start playing with simulations. These are some simulations. So what you see here is the excitation. So it's the dispersion relation of the excitation of shear modes, so transverse modes, in a liquid, going from the low temperature to high temperature. So what you see is that at low temperature, you're very close to the solid. So you see that the excitations have no gap. They disperse linearly, and then they start bending. The width is basically the line width of this mode, so how fast they decay. So what you see is that when you increase temperature, basically these things get gapped out. You see, and the more you increase temperature, the more this gap opens. You can see it much more clearly here. So this is basically similar simulations where you see that this gap opens and opens and opens and opens and opens. So this case is the case of a perfect phonon in a solid. And then what you see is that this transverse phonon is basically killed away. Okay? And what you can actually prove is that the simplest theory that I was telling you before work even at quantitative level. So you can actually track what is the position of this gap, which is called k gap, as a function of 1 over c tau. So you can measure tau as well in simulations. You have a lot of control. And you can see that indeed it follows an almost linear relation between the two. So what does it mean? Let's think about it. So tau is the average time of relaxation. So this means that if I increase temperature, I'm able to jump this barrier much quicker and to relax much quicker. I'm becoming more liquid. And what you see is that the more I become liquid, the more I'm opening this gap. So if you want, this gap is a measure of the fluidity of the system. It's the measure of how easy it is to jump this barrier and rearrange. The easier it is, the fastest you lose basically this vibration mode. So like this vibration mode. Now, let me also say that when I mean liquids, I just don't mean classical liquids. And indeed, I can just paraphrase the famous sentence of Heraclito, everything flows. And here you can see two examples where the same behavior has been observed. And let me also say one thing. It's very difficult to probe the low frequency and low wave vector dynamics of a liquids with scattering experiment. And indeed, the only experimental realization that I know of this gap that I just discussed is done in dusty plasmas. So dusty plasmas are not classical liquids, are just ionized gas that interact through Coulomb interaction or Yukawa type of interactions. And in many aspects, they behave very similarly to liquid, if you want. So at least they have a gas-like and liquid-like phase. And what you see here, this is an experiment where basically they probe this dusty plasma in two different regimes. This is the regime which is solid-like. You can see that there is an excitation. This is the map, this is the frequency, and this is the wave vector as a function of the lattice spacing, if you want. You can see that there is a propagating mode. And when you go to the liquid-like phase, you see that the weight is kind of shifted, and with a bit of imagination, you can think that there is something emanating from here. Now, we did, with my colleague in Shanghai, we did a similar experiment using what are called granular Brownian vibrators. So this is a picture of the system. This is literally a big desk with disks which are more or less half a centimeter. So you can see these are the disks. Now, you can control, basically, of course, the dispersity of this disk, and you can control the density of this disk, so the packing fraction that you are putting. And depending on the packing fraction that you're putting there, these systems, once you vibrate it and shake it, behave either like a solid or either like a liquid. And here you can see what we find. This is basically what my students extracted. You can see that if I check the frequency as a function of the wave vector in the liquid phase, I also see evidence for something that behaves like square root-like and that comes out of here. Notice one important thing. This is totally different from a thermal liquids because this is not thermal at all. So the scales that we're talking about is too large. Thermal fluctuations are totally irrelevant. So what plays the role of temperature is actually the packing fraction. So what you see here is that these things become smaller. It's not because I'm lowering the temperature. It's because I'm increasing the packing fraction. So basically, packing fraction plays the role of the inverse of temperature. But what I want to convince you with this slide is that what I'm talking about, when I think about a liquid, I'm not just thinking about water or something like that. Indeed, you can find even experiment on people. So you can put a camera on top of a crossroad, following people, and you will see that the people do a collective flows that behave exactly like a liquid. Okay? So when I think about liquid, I think like any system of many body particles or objects that behave collectively as a fluid. Now, this was the fact of the, let's say, the discussion about the excitation. What about the density of state? So the density of state is a tricky business in the liquid because it's already we can measure it. So this can be measured with scattering experiment again. You can measure what is called the dynamic scattering function, and with some bit of algebra, you can derive what is called the density of state. So the density of state of liquid, it's at high frequency. It's very complicated as in solid, so it's related to the many excitation that you have. For example, you can see this is for water. You have a huge amount of bending and twisting of all possible molecules. So this, for me, as a theorist, is not too interesting because it's too microscopic, so I cannot make a theory to encompass all these phenomena. Now, on the opposite side, what I'm more interested in is some kind of low-frequency intermediate region where in solid, as I showed you before, I expect a universal Debye law, which is a quadratic scaling. So the question is, in solid, I know there is a quadratic scaling. What happens in liquids? And so the first measurement that I'm aware of the density of state in liquids compared to something like a solid is in 1989. And let me guide you through the experiment. So this guy here is the experimental data for the solid phase. So this is a Debye crystal under 50 Kelvin. Okay, doesn't matter what kind of system it is. This is a crystal, and you can see that this is the Debye fit, but you can see almost by eyes that this is quadratic. Okay, so that fits the theory. Now, this is the liquid. And you can clearly see that in the regime where the solid is quadratic, the liquid is not quadratic at all. And it seems compatible to something that is kind of linear-ish. Now, 10 years after, these people made a smart move, and they took water, and they did the experiment slightly above melting and slightly below melting. And this is what you see. So below melting, so in the icy phase, you see indeed there is a quadratic behavior. But when you go in the liquid phase, again, this quadratic behavior seems to disappear, and the behavior becomes quite linear. So there is no trace of Debye scaling. So let me also say that this is still a very debated question. So there are many people that still do not believe in this linear scaling. But actually, colleagues from Australia, from ANSTO, very recently in 2022, proved experimentally that many liquid systems indeed show a linear scaling at low frequency. And so we were very happy because just a few years before, 1 year before actually, we published a paper claiming that this should be a universal property of liquid that comes from the fact that there are these relaxing modes around. Now, we started investigating this in a more, say, systematic way. So here you can see water. So this is water at very different temperature. This is the icy phase. You can see the density of state is clearly quadratic. You jump through a first order phase transition to the liquid phase, and immediately you see that there is a slope, and this is linear. So it seems that there is more evidence that there is a change of scaling between quadratic and linear. And this change of scaling can be understood through what is called instantaneous normal mode theory that was developed by Keyes and collaborator already in 1997, etc. So what is the idea? The idea is that I know how to deal with solids, so I don't want to get rid completely of the solid ideas. So I want to still do what is called a normal mode analysis, just looking at vibrations. But in a liquid, I can only do it instantaneously, meaning that I just do a snapshot of the liquids, and before the liquids has time to rearrange, I'm actually checking where it's vibrating. And then I do it again, I do it again, I do it again, and then I average on all these things. And that's what I get. I get what is called the instantaneous normal mode density of state. Now, if you do so, you will immediately find something very striking. You will find that not all the frequencies that you get are real. You will find a lot of frequencies which are not real, but they're purely imaginary. What do they correspond to? So this imaginary frequency corresponds to what is called an unstable mode. Remember, when you do normal mode analysis, basically the frequency are the eigenvalues of the curvature, what is called the Hessian matrix. So the Hessian matrix is just telling you the curvature, the local curvature of the potential, meaning that if the eigenvalues is positive, you are just probing a local curvature that is positive. But if you have regions where the curvature is negative, you will get something which will be a negative eigenvalues, which corresponds to imaginary frequency. So if you do this exercise for water, that's what you find. So you find the density of state, instantaneous normal mode density of state. You find that there is a branch with positive frequencies, which is linear at low frequency as well. But then you find also a huge amount of unstable modes. So don't get confused. This is non-negative frequency. This is our imaginary frequency. It's just a trick to put it in the same plot. So you need to imagine that here there is an I in front, okay? So what do you see here physically? So what this is telling you about what's happening in the liquid? So first of all, it's linear. Here it's clear, it's very linear. Now, the other thing that you can see is that if you integrate this curve, you see that the number of unstable modes grows with temperature. And this, again, it's quite understandable. It's just the fact that more temperature, you have more probability of visiting regions which are saddle or negative curvature regions. And so then the question is, what can I understand with this picture of the experimental data? This is the big question. Now, let me also do a little theory breaks and advertising. There are many theories that can derive this linear infrequency regime. So to make a summary, we believe that exploring regions of negative curvature and having eigenvalues which are negative is enough to actually claim that the density of state becomes linear and is not quadratic anymore. So this is just a little theory break. So then you can compare experiments with this instantaneous normal mode analysis. And what you can see is that at low frequency, both of them have a linear scaling. And the scaling is quite similar to each other. One thing that I want to mention is that there are differences. There are important differences. There are differences at high energy. These differences are mostly related to the potential that you're using to do the simulation. But there is also a very important difference at low frequency. And the fact is that since you're doing an instantaneous normal mode analysis, you cannot capture late time diffusive behavior. So you see that at very low frequency, the experiment is totally different as a constant value, while the instantaneous normal mode starts from 0. And this makes sense. So I shouldn't trust too much the instantaneous normal mode analysis at very low frequency because this is very late time. I'm just taking a picture, so I don't know what happened tomorrow at the picture, okay? Now, one thing which is very interesting, this is very recent, but I just want to mention it, is that you can also measure the temperature dependence of the scaling, and you find that there is an interesting universal exponential behavior. Okay, and let me just say that we don't understand this, so there is no theory explanation for this, but there is evidence that is quite robust. So this is just as a comment. So let me also say that this is still a very controversial topic, and this is more or less a good summary of the situation, and I think we are still at point 1, I would say. So yeah, let's see. There is another way, and maybe if you want a comparative way to probe solids and liquids, and it's basically based on shearing. So if you take a liquid and you put it in 2 plates and you shear it, what you will see is that the response of the liquids depends on how viscous or elastic is this liquid or this system in general. So if you have a pure elastic system, you will do this, let's say, sinusoidal deformation. The response will be exactly in phase and will be just multiplied by a number, which is basically how rigid is this system. Now, if you do it in a liquid, in a perfect ideal liquid, which I mean only viscous response, you will find a completely off-phase, 90 degrees off-phase response. And if you are in the middle, you will find something where the phase is in between 0 and pi half. Now, more importantly, what you can actually measure, and this is most of what people in rheology are doing, you can measure what is called the complex modulus. So the complex modulus is just, if you want, the response function between the strain that you are applying and the stress that you are measuring, or vice versa. Now, this is just basically linear response. So if you want, actually, this is a green function in terms of mathematical terms. And this is what you can measure. So what is the important thing? The important thing is that this object has a real part which takes care of the elastic response, and an imaginary part which takes care of the viscous response, and I can measure both of them. Now, if you look at the liquid, what you see is that at low frequency, both of these 2 parts, so the real and imaginary part, are comparable to each other. And there is a quite dispersing curve in frequency. If you look at the solid, the situation is very different. You see that the real part is strongly dominating on the imaginary part, because, of course, the dissipative effects are very small. And the response is quite flat. Okay? Now, this is interesting. And why it's interesting? Because then there is this interesting paper by Laurence Noiret. She's an experimentalist in Paris. And so the quiz is she measures something. Okay? And the question for you is, what did she measure? So here you can see this is what her experimental data show. You see that the response is completely in phase. And if you look at the response function, you see that the real part is at least 1 order of magnitude larger than the imaginary part, and it's flat. So you would say, well, it's a solid. Well, of course, it's not a solid. This is actually water. So what's going on here? Okay? So the trick is that this is not just water in a bottle, but it's water confined at small distances. So what she sees is that she put water in these 2 plates, and she starts confining, squeezing, and at a certain point, at a certain scale, she notices that the response changed completely from liquid-like to solid-like. Now, she makes sure that this is not an effect of surface. So she claims that this has nothing to do with interaction between surface and the liquid. There is not that the first layer becomes solid or something like that. So her claim is that indeed there is basically a length scale that determines if the response is liquid or solid. In other way, the proposal is that if you look at the liquid at short enough scales, this behaves pretty much as a solid. And this is, again, in agreement with just the theoretical simple arguments that I showed you before. So this is basically the paper. If you're interested, let me mention also that this is not the only experimental thing. Of course, after this paper, you see it's pretty old. She tried the same measurement in very different systems, and she finds more or less the same answer. So it looks like there is something there. And what we did also recently is we did a similar experiment where we took water, we confined on graphene sheets, and then what we did, we measured the density of state. So we were like, look, if she's right, by confining these things, at a certain point, I should see that this linear law, that this liquid-like behavior, should change and go back to solid-like. And it seems that our results are quite compatible with what she says. So you can say this is glycerol, this is water, this is more or less room temperature. And then this is the bulk sample, OK? So you see that both bulk samples have a linear slope. This is the density of state as a function of frequency. So this is what I would call liquid-like. And then what you see is that by confining these systems, you see that this slope starts basically moving up. And it doesn't reach exactly the Debye law, but it becomes pretty much close to the Debye law. And so what we're claiming here is that by confining the liquid, again, this response or these dynamics at low frequency starts to become solid-like, starts to follow more Debye theory rather than liquid or fluid dynamics. And this is compatible with Lorentz-Noiré results. Now, before moving on, let me just flash for a second the heat capacity of liquids. So the heat capacity of liquids has one important property. It decreases with temperature. So it's not only quantitatively different from a solid, it's completely qualitatively different. So remember, the solid goes up. It goes like T cube, and then it plateaus. This is what you find for liquid. So this is the density, the heat capacity of various liquids, xenon, argon, et cetera, And you see that there are two properties. One property is that definitely it decays with temperature. And the second property is that it seems that the slope depends on the system that you're looking at. So the questions for a theorist are two. Is, first of all, why decreases with temperature? And second, what determines the slope of this decrease? Now, there are two theories accepted for this. So the first theory is the most famous one. It's called the phonon theory. And it goes back to what I just told you before. So remember, increasing temperature, these modes, which are solid-like, get away. So what does it mean? It means that if you believe that each of these modes is a carrier of energy, increasing temperature, you're basically removing carriers of energy. So if you actually do a computation, what you see is that increasing temperature, you lose carriers, and therefore the heat capacity starts going down. You have less ability in transporting energy. This is one theory. The second theory, it's more related to these unstable modes that I was talking about, and it's basically the idea that this decays in temperature is related to the raising of these unstable modes. So the mode, if you want, is the complementary view. And indeed, I deeply believe, and this is not proven yet, that the truth is actually in the middle, because basically where this shear wave disappears is where this unstable mode grows. I couldn't prove it yet. I'm actually trying, but that's what it is. But let me say that still the situation is that a complete and widely accepted theory of heat capacity of liquid is still missing. And I'm not talking about some very exotic property. I'm talking about the heat capacity of whatever simple liquids. And we don't know how to explain it. It's quite amazing in 2024. Now, in the last 10 minutes, let me discuss with you a slightly different topic that will try to connect a bit with what high energy and astrophysics and black hole people are doing. And so the thing that I want to discuss with you is, let's take a liquid, and let's think about some properties of a liquid. And the question is, can these properties and take whatever values they want? Like imagine a transport coefficient, like the viscosity, for example, that I'm discussing right now. Can the viscosity of a liquid be whatever? Or is there some bound from physical argument of this viscosity? Now, why this relates to black holes and astrophysics and gravity? It relates because, so in 2001, there was a paper by this gentleman that claim that using some fancy field theory that are related to black holes, I will tell you in a second why they're related to black holes, they can prove that whatever system in nature that you can consider, the viscosity divided the entropy of this system has always to be larger than this number here. So here you can see this is a quantum bound, so it can actually be derived in a less formal way from the Heisenberg indetermination principle. And what these people claim is that basically this it's related to the fact that there is a minimum time scale that is basically allowed by quantum mechanics. Now, if you do, you do experiments and you try to check if these people are right or not, this is what these people are claiming. And these are data from different systems. So this is water. You can see there is a minimum, but it's quite far away. It's actually 30 times larger. Then you go to helium, and it gets a bit smaller. You can go to more exotic things. These are ultra-cold Fermi gas, and this is quark-gluon plasma. So this is basically the plasma that is produced in this heavy ion collision when you take these heavy atoms and you squash them together, and you produce like a soup of deconfined quarks and gluons going around. You see, this is actually the closest systems that we know from this bound. And the belief is that the more strongly coupled the system becomes, the closer you are getting to this bound. Okay? Now, this is interesting because it connects various things, and let me just flash why this has to do anything with black holes and gravity. So how these people found actually these results. So they found it using what is called ADS-CFT correspondence. This is like a theoretical framework that was discovered in the context of string theory in 1998. And to make it simple, the idea is that there is a duality between gravitational theories and quantum field theories. So somehow, if you have a problem written in terms of some quantum field theory, you can map it back in terms of gravitational degrees of freedom. And you can basically solve or compute whatever you want to compute in your quantum field theory using gravity. Okay? So this is the idea. I'm not going too much into the details. But let me say one thing which is important, that the idea that gravity and fluid dynamics have a lot in common is definitely not new. And indeed, you're probably much more expert than me, but most of the models in cosmology are based on fluid dynamics, basically, or ideal fluid stress tensor, etc. And also, one thing that I want to mention is that indeed the dynamics of black hole horizon, it follows hydrodynamics equation of motion. This is known as the membrane paradigm, and is highly used. And other things that I want to mention, since many of you are working on gravitational waves of these big bodies colliding and whatever, the patterns, if you want, of gravitational waves and shear waves in liquid is extremely similar. Indeed, a shear deformation in a liquid is nothing else than, if you want, a polarization, a graviton. It's basically a graviton polarization. Okay, it's a tensor to object. Now, let me also say that if you're curious about this is some self-advertising. The main idea is of using gravity to solve other problems. And indeed, we have already learned a lot about hydrodynamics. So here you can find this little book that I wrote where you can try to see how this actually works. And this is one example where we summarize many of the things that we learn in hydrodynamics using gravity. I find it pretty cool because it's very interdisciplinary. Now, let me also say one thing that I mentioned is that these bounds that I mentioned about the viscosity, it's very similar, or it's in spirit equivalent, if you want, to a bound on a time scale, which is called the Planckian time scale. So the idea is that whatever you are doing in nature, time cannot be smaller than the time scale. And this time scale, you see, is h bar divided kBt for a thermal system. And again, you can derive it from the indetermination principle. It's just there. Now, let me say that these scales plays a huge role in many areas of physics. And here I choose two of them. So one is condensed matter. These are very exotic systems. These are called strange metals. So these are metals that do not follow the laws for metals, and in the sense that their resistivity is linear instead of quadratic in temperature. And they are a big deal for solid-state physics right now. And why they are important? Because if you actually apply a quite standard analysis of the scattering time of the electrons in these systems, or of the quasiparticles in these systems, you find that all the scattering times are similar to each other, and they are basically given by this. So the linear anti-resistivity comes from the fact that the scattering time follow a Planckian law. Now, in the context of things that you are very familiar with, this Planckian bound also plays a role. And indeed, these Planckian bounds appear in many of the theoretical descriptions of black hole physics. And here you can see one proof, experimental proof using LIGO and Virgo data, that one of these bounds seems compatible with actually the data. So I encourage those of you who are actually expert in this to have a look at this. Now, what I want to say before concluding is that the fact that there is a bound on the viscosity of a system can be derived also from classical grounds. And the reason why there is a minimum in the viscosity is just the fact that the dynamics of a fluid system cross over between something that is liquid-like to something that is gas-like. So if you go at high temperature, the viscosity comes from the fact that the particles are actually colliding between each other. If you go at low temperature, the dynamics change drastically. This is like liquid-like, and the viscosity is not anymore collision. The viscosity is basically relaxation over jumping barriers, and this is why you have this exponential factor. Now, if you put these two together and you just equating them, you will clearly see that there is a minimum in the middle, and that's what you see in many systems. The funny thing is that if you apply standard classical arguments, you can also find that there is a minimum in the viscosity, in the kinematic viscosity of liquids. This is a paper, a nice paper in Science Advance by some of my colleagues. And if you put the numbers, you see this is a very simple formula. It's similar to the bound that I was mentioning before. It's not exactly the same. If you put the numbers, you find that the viscosity at the minimum of every liquid should be more or less of the order of 10 to the minus 7, and this is what you find. So you see these are very different liquids. Of course, the viscosity of the liquids can go a lot of order of magnitude around, but if you look at the minimum, all the minima are more or less order 1 in terms of this scale. So there is something universal there. And let me also say that this is not only for classical liquids. So we did the computation for coagulum plasma. It's a liquid. It's a very high energy liquid, but still it behaves like a liquid. Now, what is funny here is that you have to be careful. So what is universal is not the shear viscosity itself, is the kinematic viscosity, so divided by the density. So the viscosity of the coagulum plasma is actually enormous. So this number here, it's enormous. It's comparable to this window. But once you divide by the density, which is also enormous, funnily enough, you find a number which is roughly compatible exactly with the number for classical liquids. So this is, we suggest there is some similarity in the dynamics that this, but it's an open question why complete different systems show all the same number there. Now, what is also interesting that we started to say, okay, well, for the viscosity works, what about something else? So we check thermal diffusion. So thermal diffusion compared to the viscosity is not the diffusion of transverse momentum, it's the diffusion of energy, so it's completely different dynamics. We put it together, and what we find is that not only the minimum of thermal diffusion is universal, but it is actually, at first approximation, exactly the same number of the viscosity. So viscosity and thermal diffusivity are completely different objects. At the minimum, what you see is that they are roughly the same. So from theory, we can basically, with very simple arguments, show the equality between these two. And here you see the data. So these are experimental data for 3 different systems. I don't remember which one of the viscosity and which one is the thermal diffusivity, but the dash is one and the other is the other. And you can see that at the minimum, all the systems are very, very, very close to each other. So this is also a quite suggesting, let's say, case. And yeah, this is just to conclude. The conclusion is that solids and liquids are actually much more similar than what we expected if we don't restrict to small frequency and small wave vector. And this is also, or equivalent to late time and large distances. The idea is that maybe the question itself that was at the beginning was not trivial, but was actually not well posed. It's not even clear if there is a difference. So when I ask you if there is a difference between liquids and solid, maybe the correct question is asking if there is a difference at which time scale and at which length scale. It's difficult, if I don't tell you this, it seems it's very difficult to put just a line in the middle and say this is liquid and this is solid. So this opens a bit the question whether there are really different phases of matter with completely different dynamics, or actually if the conditions that you're looking at or the observational time and whatever matters. And I want just to finish with the fact that, even if this looks like a simple question, if you want to divide, gases, liquids, and solid, it's actually much less trivial than what expected. And I hope that I convince you that some of the questions that, in principle, you would have thought are solved in the context of classical liquids are not solved at all, and people are still fighting nowadays in conferences all the time. So with this, thanks a lot for listening, and I'm open for questions.
Thank you very much for this really beautiful talk. I have a question. When we see phase transitions between liquids and solids, so doesn't this give us a line where in some of these phase transitions, if heat is being released while there's no heat released when it's a solid or when it's a liquid, but you have this specific part where you have heat release?
So let me see if I understood the question. So
with a phase transition from liquid to solid, you also have some heat release as well.
Yeah, these are usually this is first order. Yeah. So that's true. So regarding the heat capacity that I show you, these data here are taken above there. So if you go, if you have a first order phase transition, like in a standard melting, you will definitely have some kind of, a jump in the specific heat. But here you're looking at after. These I'm looking only at the liquid phase.
Then my question is, does this define boundary between liquids and solids when you have a phase transition?
Yeah. So you're definitely right. There is a phase transition in the term. What is not obvious, it's basically what you call liquids and solids. So how much of these dynamics you attribute to solid, how much you attribute to liquids. But indeed, there is a phase transition, first order. But usually you see, in terms of phases, it would be nice to have something which is more like second order. So it's more like related to some symmetry breaking or something like that, and not directly first order. But you're right. There you can definitely distinguish what is left and what is right. These things is jumping. That's correct.
Thanks. It's a lovely talk. And I'm supposed to teach digital mechanics to 30 students, and I had no idea that temperature of liquid, the heat capacity of liquids wasn't properly understood. So, and I will say students don't ask me these questions, and they should. That can't be at atmospheric pressure. All of those are gases, and that goes up to
yes.
SDP. What pressure was that?
Yeah, so you're totally right. So here I cheated a bit. These are actually in the supercritical regime. So these are high there, where actually there is no clear transition between the gas phase and the liquid phase.
And they're at the supercritical point, or they're into the supercritical regime?
They're above.
Above, yeah. Okay. Yeah.
But let me say that this is not necessary. So I took that just because I copy-pasted those data, but you can see the similar behavior for all type of liquids. So it's a universal behavior, the fact that these things goes down. And in this paper here, they compared, I think, something like 20 or 30 different systems, and you see that basically they all go down in the same way.
And the fits are just 1 over T, or the fits are a bit more?
No, so the fits is a bit more complicated. That's a good question. So to my understanding, there is not a clear power law. So it looks like, I have to say there's very little, but yeah, there is no clear power law. So it's not just some kind of 1 over T or 1 over T square. So yeah.
So in some solid state mechanics that are more anomalous, there are some people looking at fractal media, and there they use like graph Laplacians that are defined topologically. So like say if you want to define like the Laplacian for like wave and heat diffusion in the material, or any other differential operator, you do it in mostly like topological terms. But in liquids this is clearly not true, because like topology like deals with what's connected to what, and that's no longer true, mostly in a liquid. So am I correct in understanding that like in liquids you use more like dynamical tools, or instead of looking at what connects to what, you look at like characteristic times of how long like does such transition take to happen? Yeah, just making me wonder like how to connect them.
Yeah, so I think in solid, of course, it's much easier to make a connection with structure or links, like you're describing, like whatever local topology of links, bondings, or whatever. So there is a clear connection, if you want, between the microscopic so just literally in terms of atomic dynamics, and the macroscopic. So I can do a description in terms of collective phonons, but I can basically connect them very well. In liquids, this connection is much less clear, and indeed, fluid dynamics is usually based on coarse-grained description. So I don't look at the particle, I look at the collective velocity field, and I see what happened to that. Now, part indeed of these questions is, can we still understand liquids in terms of an atomic description? And then indeed, that is much more complicated because there's no structural order. And one possibility, which I think is quite fascinating, and this is related a bit to also topology, that what you're saying, is that maybe there are hidden orders, in the sense that there are some kind of orders that you cannot just see by eyes, but they're basically emerging through other different quantities. But definitely, yeah, I'm not sure you can start from a very structural definition, yeah.